Project 1 by Sunwoo Kim,
Alan Benjamin.
And Josh Klein.
So the question we're solving is question number 1, which is SpaceX launches a rocket of mass m off the edge of a cliff of height h. The rocket produces a constant thrust force of unknown magnitude that is directed at an angle theta above the horizontal. Unfortunately, the rocket crashes into the ground at distance d from the base of the cliff. We must determine the magnitude of the rocket's thrust force and the speed of the rocket when it crashed, and include a graph of the position with respect to t. In essence, we are solving a general projectile motion problem with the exception of implementing thrust into our calculations to determine the thrust force and speed of the rocket before crash in terms of other variables. So description and assumptions. So we will be solving everything in terms of other variables using the following: d for distance, h for height, the acceleration in the x direction, acceleration in the y direction, the force of the thrust, force of gravity, m for mass, the initial velocity, which is 0. We're trying to solve for final velocity. We have angle as theta and t for time. And the assumptions that we are making is that there is no air resistance, and that we know that the rocket accelerates downward because it crashes into the ground at some point after it is launched.
What you see here is some previously unreleased footage of the actual launch of this SpaceX rocket. As you can see, as soon as the engines ignited, it became apparent that the thrust force was not strong enough, and when the rocket reached the Alright, so this is the final solution we came up for the force of thrust. And for the calculations, we started off by listing our knowns and unknowns and our assumptions, and then started with the sum of the forces in the x direction. To determine the acceleration, we just divided by the mass, same for the y direction. And then for the position versus time, we just used the kinematics equation for final position and plugged in some of our knowns and unknowns, and then solved for time, which we got here. And we were able to do that since we knew that the final position in the y direction was going to be 0, since it ends crashing into the ground, and the initial position was h, as represented in the diagram here. Then for the x direction, we used d as the final position, because that was the distance that it traveled from the cliff, and then plugged in our knowns and unknowns. We came up with this equation, which relates the thrust force to the distance from the cliff, the mass of the rocket, gravity, and the angle of the thrust force. Okay. Next thing that this line here is just a unit check, which you'll see in the next slide. And the next thing that we needed to find was the final velocity, which we used this kinematics equation. V final squared equals V initial squared plus 2 times the acceleration times the displacement. We know all of those values from the equations above, so we plugged those in to find the final velocity for each of the x and y directions, and then used the Pythagorean theorem to determine the magnitude of the final velocity, which through some more algebra, we came up with this, which is on the next slide. Yeah, so this is the equation that we found for final velocity, and it's in terms of the distance again, the acceleration due to gravity, the angle of the thrust force, and the height of the cliff. So for the part 3, where we were finding the position versus time graph, we used Desmos and some sliders so that we could show how the different variables affect things. For the x position versus time, you can ignore the negative part of this graph. But we have these different sliders that we can adjust. So A is representing the angle, and you can see that as we increase the angle closer and closer to pi over 2, that the x position with respect to time grows less and less quickly. And when it's pi over 2, it's hardly changing at all. It shouldn't be changing at all, because that would mean that the angle of thrust would be going straight down, and the rocket would just be accelerating only in the y direction. Another factor we can increase is the force. This is representing the force of thrust. And you can see if we have less of a force of thrust, then it's not going to accelerate as quickly. And if we have more, it'll accelerate more quickly. So these are all things that we would expect. Similarly, for the y position, you can do the same kinds of things. And you can see things changing. If we increase the force too much, it'll actually start rising with respect to time, which you can see here. But we were assuming that the force would not be that high, because in the problem we read that it was going to crash into the ground.
Okay, so for checking our solutions and making sure they made sense, we used the interactive position graph from the last slide to relate all the variables and make sure that the changes were proportional to the correct values, and it ended up all making sense when we plugged that stuff in, so that was good. And then we also did unit checks on both of our solutions, and you can see here that for our force of thrust, when you put the units through, it checks out and equals newtons, which it should for thrust. And then on the next slide, you can see that for our final velocity, when you plug all the units in, it comes out to meters per second, which is also correct. So both our unit checks and our position versus time graph went towards the fact that our equations seem correct. So for our reflection, we compared this problem to other problems that we've done in this class. And for the similarities, we came up with that it's very similar to projectile motion because it's using similar formulas, and we also broke the problem into the x and y components. So the solution strategy that we used was very similar. The main difference between this problem and other problems we've done with projectile motion is that this isn't projectile motion because it has the added force of thrust. So there's acceleration in the y direction other than gravity. So it's not just a projectile motion. And there is acceleration in the x direction as well. So we had to incorporate this force into our calculations, which made it a little more complicated, and our formulas ended up being quite a bit more complicated when we ended up with our final results. Thanks for listening.